I'm here to present the 2023 edition of the CARLA Autonomous Driving Challenge. Let's just drive into it. So first of all, I would like to thank our sponsor, AWS, FutureWay and Synchrotron for the great generosity and support. Without their support, the CARLA challenge will be impossible. So it's a complex competition that requires a lot of computation. Their support, their donations is what really runs the CARLA Autonomous Driving Challenge. So thank you very much for supporting the community and supporting the challenge. I would also like to take a second to thank the organizers of the challenge. So this year, Guillermo, Joel, Yushi, Songyan, and Danlen helped to put this together. So this is a very complex challenge that requires of a sophisticated cloud infrastructure. Really, the guys did a great job to put everything together. So this year's challenge is done in collaboration between the Embodied AI Foundation, Synchrotron, and Eval AI. So thank you to all of you for helping organize the challenge. Now, some of you might have been to previous edition of the challenge, but for those of you who are new to the CARLA Autonomous Driving Challenge, I would like to give you a brief explainer. In a nutshell, the CARLA Autonomous Driving Challenge serves as a sort of open testbed to evaluate autonomous driving agents on driving proficiency. For us, driving proficiency is basically driving from starting position to a destination through a route. So basically, you are provided with a set of waypoints, and you need to follow those waypoints. During that route, your agent is going to be encountering complex traffic situations, the same type of traffic situations that we human experience throughout our driving life, right? So all of this is happening on a set of common maps. The database of traffic situations is also common. We're using common metrics, meaning that every single agent is evaluated under the same set of metrics and under the same conditions, trying to basically develop this test bed so that we can understand which techniques, which approaches are better for certain situations. This is aimed to accelerate progress in the research community. Typically, at the end of the year, the winner of the competition tend to release their stacks, and then teams the year after are able to start from there and keep building better solutions on top of whatever has been made open. So this competition is open to researchers, engineers, and enthusiasts, and it's completely for free. So basically, we take care of the infrastructure so that you can bring your best work and keep making progress in the autonomous driving community. So let's talk a little bit about environments. In the 2023 competition, this is the type of environments that you're going to find in challenge. So you're going to find a diversity of areas, including highway type of areas with multiple lanes, heavy traffic, complex junctions and intersections. You're going to find urban areas with high buildings, suburban areas with all the elements that you typically find in those places, and even countryside environments. So we give all participants access to a set of towns. Town 12 is our default map for training. This is provided so that people can develop and train their models. It's a map that encompasses more than 100 kilometers square. We provide 90 default routes spanning around 700 kilometers, which is equivalent to like 30 hours or so of real-time driving. But the reality is like these routes are so packed with traffic situations, with traffic scenarios, that probably they're equivalent to 10 to 100 times more driving time. So they're really packed with very, very exceptional situations. Then we have the validation map. Town 13 is also provided for the sake of validating agents. So after you have trained or developed your stack on the training map, you can use the validation map to double check that you haven't been overfitting the town 12. So this one is also of the similar size. of 100 square kilometers, and we provide 20 validation rounds spanning more than 200 kilometers. Finally, the CARLA challenge, the official evaluation happens on town 14, what we call the testing map. This has similar size of the previous towns. We have 20 routes spanning more than 200 kilometers and an equivalent of 9 hours of real-time driving. People don't have access, teams don't have access to this map. This map is kept secret in our data centers to make sure the evaluation is fair. When you participate in the challenge, you can subscribe to one of these two modalities. The first modality is the sensors track, which basically means that teams can set up their own sensor stack, choosing between a predefined set of sensors. There are some limitations here in the number of sensors that we allow you to use for just computational and budget issues. So, but we are working on extending this number, increasing this number in the future. There's also a map track, which basically gives you access to the aforementioned sensors, plus an HD map that you can use to simplify navigation and planning. We evaluate agents using something called driving score. Driving score is a combination of two terms. The first term is basically the percentage of route that your agent has completed. So we average the completion of all the routes. That's the first part of the scoring formula. The second one has to do with the type of infraction and the number of infractions that your agent has made. So each infraction has a penalty score associated with it. For example, in the case of colliding against a pedestrian, your score will be divided in half. So every time you have one of these infractions, we're basically discounting your final score proportionally to the penalties that you see on this table. Something important to highlight is like the 2023 CARLA challenge brings new type of infractions, such as failure to maintain minimum speed. So there are certain areas where you are actually required by law to maintain certain speed. That's something important. Also, failure to yield to emergency vehicles, which is something that we'll have to do in normal circumstances. And also a scenario timeout. So there are certain situations that your agent is required to complete under a time limit. If you are not able to complete the scenario under a time limit, your score is affected. Traffic scenarios. So in the challenge, we have a plethora of the scenarios, moving from simple stuff like changing lanes in dynamic traffic, to yielding to traffic on a roundabout or at the intersection, to something more complicated like anticipating behaviors, adversarial behaviors, like in this piece, where a vehicle ran a red light and you have to react and stop last second. So this year, we have extended the database of traffic scenarios quite significantly. Now we have new dozens of new types of scenarios that can be instantiated, giving rise to thousands of variations. So some of my favorites involve dealing with construction areas, for example, this one at the bottom, where you have to find your way around a construction area, coping with the traffic on the adjacent lane, or yielding to emergency vehicles, or pulling out of a parking space with heavy traffic. These are things that we all have to do on a daily basis, and now these are also part of the CARLA Autonomous Driving Challenge. Let's take a look at some of my favorites. So let's see what the blocked lane and because of construction looks in practice. So you have the ego vehicle. The ego vehicle eventually finds that the lane is blocked, but there is traffic on the adjacent lane, so it has to wait for an opportunity to kind of like change lanes and proceed. Easy. Then we have another scenario where the ego vehicle has to yield to an emergency vehicle. So in this context, the ego vehicle eventually sees that there's an emergency vehicle behind it, change lanes, and allows the emergency vehicle to proceed. So some of these traffic scenarios require very good perception capabilities. So that's what makes the new CARLA Challenge 2.0 that complicated and challenging. And now let's move to the 2023 results. So we received 50 team applications, and out of these 50, we approved 20 teams. Out of these 20 teams, we received more than 100 submissions. These submissions result in more than 10,000 of simulation and an equivalent of 4,000 kilometers driven. So there's a lot of compute spent to evaluate all these stacks. And this is what we were all expecting. So for the sensor track, the winner of the CARLA Challenge 2023 is LRM with a driving score of 1.23. In second position for the sensor track, we have Turing and AI team with a driving score of 0.58. For the map track, Kyver end-to-end takes the lead with 3.11 points in driving score, and LRM scored second. There were many submissions, many teams that decided to submit an entry into the leaderboard, but unfortunately, not all submissions were made publicly available, were made visible. Based on this, we have made the decision that for future competitions, all submissions will be made publicly available, so they will be visible to the community. And I will be talking more about this in a few minutes after the team's presentations. So, coming back to the two tracks, I would like to congratulate the winners for their success and also all the participating teams. We understand that this is a very complex competition. It really has increased the level of difficulty with respect to the leaderboard 1.0, and it's quite normal to start with low driving score during the first years of the competition. So if we compare the leaderboard 1.0 throughout the different years that we have been running it, so we also started on our first year with relatively low driving score. So the best performing team wasn't able to even get 9 points of driving score. And throughout the years, we have been doubling and tripling this score consistently. So this is the first year that we ran the leaderboard 2.0. So the new CARLA Autonomous Driving Challenge is based on the leaderboard 2.0, which is an extension of the previous leaderboard. We have started with a best solution that produces a driving score of 3 points. We really expect that in the upcoming years, the performance of the different staff will be increasing significantly, doubling and tripling. So this is a message for all teams to not give up and keep trying and keep making improvements to the stack to be able to succeed in this new version of the CARLA Autonomous Driving Challenge and the Leaderboard 2.0. Don't give up. And now we're going to hear from the presenters, from the winners of the two tracks about their approaches and how they cope with the competition. The first presentation is by LRM, by Luis Rosero, Iago Gomez, Andre Prewodowski, Junior Silva, and advised by Dr. Dennis Wolf, Professor Fernando Osorio, and all from the Laboratorio de Robótica Móvil, ICMSC, USP, São Carlos. Congratulations, LRM, and let's hear about your approach.
Hi, my name is Luis Rosero. We are the LRM team with Iago, Junior, Andre, and our advisors, the Professor Fernando Osorio and the Professor Dennis Wolf. Uh, we are with the Mobile Robotics Laboratory at the ICMC of the University of Sao Paulo at São Carlos, Brazil. I am going to present our entry for the track sensors in the CARLA Autonomous Driving Challenge 2020, 2023. Modular pipelines have been used for a long time in autonomous driving with great success. They are popular along with the use of high definition maps. In this slide, we can see the typical structure of a modular pipeline composed of localization, decision making, planning, and control modules. This autonomous driving approach has excellent results but depends on the use of MF. Without this, it fails. With the recent success of deep learning, one option to modular pipelines is end-to-end driving. This approach maps raw sensor directly to brake and throttle signals, or to other intermediate signals such as speed or steering angle. In this approach, almost all the modules of a modular pipeline are reduced to a single module. This approach is more indicated in the case of navigation without a map. High-level commands can be used at intersections to avoid ambiguities. For example, the command turn left or turn right. This is the case of the track sensors in this challenge. Considering the above, we propose an approach that takes advantage of the previous two. Then we divide motion planning in two subtasks, lateral planning and longitudinal planning. For lateral planning, we use end-to-end learning to regress a path. That is followed by a low-level controller, and finally generating the steering signal. For longitudinal planning, we use a traditional modular pipeline with a very robust perception module that fits a state machine for decision making, whose output is a reference speed. That is followed by MPC controller. Using this method, we ranked first in the CARLA Autonomous Driving 2023 for leaderboard 2 in the track sensors. This diagram represents the lateral planning. In the first stage, we have the reading and fusion of the data coming from a LiDAR sensor and stereo camera. Then they serve as input for an end-to-end model that regress a set of waypoints followed by a controller, and finally it calculates the steering angle. Here is our end-to-end module for path regression. This figure shows how all the information is transformed into bird's eye view space. Raw perception transformed from the sensor coordinate system, and high-level command poses transformed from the world coordinate system. Each high-level order is represented by a colored point. Follow the lane is green, left is red, right is blue, and straight is white. All this information from different coordinate systems is merged in the bird's-eye view space in the form of rasterized RGB images. This fusion, the nine channel image, is the input for a convolutional neural network. That is trained to regress 200 waypoints spaced every 20 centimeters. It is in the bird's eye view coordinate system. Then we need to transform that resulting path back to the world coordinate system to navigation purposes. Finally, that path transformed to the coordinate system goes to a lateral controller, which is an MPC controller, and calculates the steering angle. Now, on the other hand, we have longitudinal planning. It is a traditional modular stack. The input is data coming from LiDAR sensor and stereo camera. First of all, we have a perception module that detects all the objects in the scene, including cars, bicycles, and pedestrians, as well as traffic lights with their status green, yellow, or red. For dynamic objects, the perception module performs tracking and prediction. Then we have an assessment module that evaluates which of these obstacles is the most important to continue with the navigation, and send it to the decision module that defines a reference speed based on perception. That speed is followed by a control module and calculated throttle and brake values. For the perception module, we use point pillars plus sort to detect and track dynamic objects in point clouds. For segmentation of instances, we use mask RCNN. We fuse the detected instances with the point cloud generated by the ELAS algorithm to have the objects detected in 3D in 3 dimensions. The risk assessment module selects which objects detected in the previous stage are important based on the intersection of their area with the area surrounding the path. As seen in the figure, the path has 2 surrounding areas: red area for dangerous detections, and yellow has a warning area. When an object is detected in red area, the ego must stop, and in yellow area, the object is tracked. Objects whose area or predicted path does not have intersection with the area of the path are not considered in this time. The decision-making module is a more finite state machine. The inputs are defined by the previous module and have a binary encoding. 00 when there is no obstacle in the path, 01 when there is a dynamic object being tracked, 10 when there is a traffic light, red, on 11 when there is a stop sign. Finally, the reference speed is followed by a PID controller that calculates the throttle and brake signals. For dataset collection, CARLA permits a set of realistic and calibrated sensors. We use this sensor layout in the simulated vehicle for our agent and for data capture. We use one LiDAR, one GPS, one IMU, and two cameras for the stereo camera. To train our path planner, we use ResNet 18. The dataset is composed by RGB images for the virtual view space. We save stereo and LiDAR in the virtual view. The ground truth are 2000 waypoints. All datasets are collected from CARLA simulators from Town 1, Town 3, Town 4, Town 6, and Town 11. For instance, segmentation, we use mask RCNN. The classes used are pedestrian, car, and bicycle. The labels are saved in the COCO format. For 3D detection, we use point pillars. We use the same classes for instance segmentation, and the labels are saved in Kitty format. The results, we achieved the highest score in the main metric that evaluates the leaderboard 2, driving score. We also had the highest score in other important metrics such as collision vehicles and collision layout, which shows that our modular pipeline is very effective in the perception task for avoid collisions. Thank you very much.
Great talk by Luis. And now we move on to the second talk by the Kyver end-to-end team, the winners of the map track, with Kashra, Rishi, Mohammed, Elhambiwi, and White Sang from the NOAA's ARC laboratory, Huawei Technologies. Let's hear from them.
Hello, my name is Kasser Rizai. I'm presenting the submission from Kyber E2E team to the CARLA Autonomous Driving Challenge 2023. I'm presenting on behalf of myself and my colleagues from the NOAA's ARC lab, Huawei Technologies. Here's an overall architecture of our submission. In terms of sensors, we are using 3 cameras, LiDAR, radar, GPS, IMU, and odometer. The map, HD map, of course, is provided through the CARLA. We do a localization of the ego based on the GPS, IMU, and odometer, and then this localization is passed to various modules. Our perception is 2 parts. There's a 3D object detection that uses the camera, LiDAR, and radar to detect a variety of objects. There's also a language-aided perception, which is mainly used for traffic sign detection. We do a post-processing of the detection based on the map data to improve the detections and then pass the detection result to tracking and prediction. Our detections are zero-shot detection. They don't have any temporal information. So we first track the objects to match them from one frame to the next, then use a Kalman filter to estimate the temporal aspects of the objects and perform a prediction to find the position of objects in future. This information is passed to the planning and control, where a behavior planner calculates high-level decisions for the agent, such as negotiation and lane decision, followed by a motion planner that calculates the trajectory for the car to follow, and a controller that estimates the control action for the car. Our perception in two parts. The first part, as I mentioned, is the 3D object detection. This is a modified variant of the transducer backbone along with a center net head. It's trained from scratch with data collected from Leaderboard 2.0. The input to this model is a bird's eye view localization of the LiDAR point cloud and a front-facing camera, and the output is the position, orientation, size, and class type of the detected objects. Our language-aided perception uses some pre-trained models for object detection and scene context estimation, and it's mainly used for detecting traffic signs and their state. So we leverage a separate higher resolution front-facing camera with narrower field of view as input here. We use the zero-shot first-person view 2D object detection model combined with a visual question answering model to estimate the context. So we basically take the front camera, this high resolution camera, use a prompt to detect objects within this image, and then crop the images and use another prompt on the visual question answering model to extract the context from that scene, which in this case, for example, can be find the speed limit sign, and then from the detected speed limit signs we ask for the value written on the sign. In terms of the tracking and prediction, we are using an uncentered Kalman filter with a bicycle model alongside an unbalanced linear sum assignment to track the objects over time and effectively filter the noise and improve the robustness of the detection. In terms of prediction, we are using a very simple constant speed prediction. So if the objects are moving along the lane, our assumption is that it's constant in speed along the anchored path, so the objects will follow the path. If the objects are crossing a lane, we do constant speed with constant heading. So our planning and control, at a high level, we do the behavior planning, which consists of negotiation and lane decision. So for negotiation, we first make a decision for each object whether to yield or not. We use the state machine to track each object and also make assumptions on their future acceleration based on game theory. And we alter the predicted trajectory of the objects according to the assumed acceleration and yield decision for that object. For the lane decision, we are using a heuristic to obtain EGO's high-level lane action based on the scene and also some aspects of the state machine. Our decisions are like keep lane, change lane, in-lane avoidance, etc. So our motion planning, we are using sample-based motion planning. We are first generating a number of trajectories with 3 degrees of freedom in frame that are conditioned on the lane decision. The 3 degrees of freedom are longitudinal, lateral, and time dimension, which is effectively the SLT space. Then we choose the trajectory with the best cost. Our cost function consists of swiftness cost that encourages the car to go faster, closeness to the reference path to make sure that we follow the path, longitudinal lateral jerk to basically result in more comfortable and more smooth trajectories, and the safety cost to avoid collision. Of course, there are a bunch of parameters in this cost function that needs to be tuned, and we employed inverse reinforcement learning to learn these parameters using expert trajectories from open source data sets. In terms of the controller, we decoupled the controller into lateral and longitudinal control, and we used a simple PID with feed forward compensation for the control task. So quick introduction about how the inverse reinforcement learning is done. This is a typical, basically, inverse reinforcement learning approach. We were using we adapted the maximum margin planning for this task. We take the expert trajectories, we generate candidate trajectories along the different dimensions. We optimize the cost function, basically find the trajectory that optimizes the cost function combined with a margin term. We calculate a loss L that tries to lower the cost for the expert trajectory and increase the cost for these sample trajectories. By taking the gradient of this loss function with respect to the tunable parameters, we are able to calculate the parameters that would result in a chosen trajectory that's closest to the expert trajectory. This margin term ensures that the cost of a non-expert trajectory that is different from expert trajectory is at least higher by the margin term. And in terms of the actual optimization, we assume the non-reactive dynamic objects. Therefore, future position of other objects would remain the same irrespective of the ego's action. As a result, we can do very quick evaluation of various outcomes and quickly estimate, do a quick simulation of the environment. This is the result that we achieved from the secret test cases, and we got a driving score of 3.1 overall on the map track. So these are some sample videos that I'm showcasing in terms of the behavior of the model. This is an example of a car with open door. So we find a gap between the car with open door and incoming traffic and pass through there. This is an example of the in lane being blocked. So we make a lane change, pass the object, and return to our lane. You see here how the car finds a gap in the incoming traffic to come out of the parking, and when there's another car cutting in, it slows down to avoid collision. And here's a pedestrian emerging from behind a car, and then we stop for the pedestrian accordingly. Here is an example of making a right turn at an intersection with crossing traffic. So we slow down and find a gap between the incoming traffic and merge into the incoming traffic. Here's an example of the incoming vehicles invading the ego lane. So the ego basically shifts to the right a bit to bypass those objects. Here's a case of the slowing down after the car in front performs an emergency brake. And here's a case of driving on the highway, merging into traffic and yielding to the traffic as well. I also wanted to mention that these videos are recorded at twice the real time. So what you see is actually faster than the actual realistic playback of the scene. So these are some of the challenges and issues for submission. Of course, there are certain limitations with our perception, specifically that it's very sensitive in crowded scenes when there are lots of cars on the park side and there's lots of cars on the other side. It generally has lots of false positive, which makes it a little bit too conservative at times. In this example, there's a lot of vegetation around the road, and our perception actually detects these bushes as pedestrians, and basically the car stops for that pedestrian indefinitely. And this is a case of the limitation of the heuristic high-level action decision. Now, when we see a car on the road stopped in the middle of the lane, we assume this is a traffic congestion, so we don't make any attempt to bypass that car. In this case, of course, the planner cannot distinguish this car that's stuck in the middle of the road compared to congestion, so it just waits behind that car indefinitely. So in terms of the future work, of course, there is room for improving the performance of the perception module. And also, we can improve the planning and make it a bit more conservative to account for occlusions using phantom objects, and make sure increase the safety of our planner. Thank you for your time and attention to this talk.
Great talk. Now, moving on to what's happening next in the CARLA Thermos Challenge before we move to the Q&A session with the authors. So some announcements. For the 2024 edition of the CARLA Challenge, we'll have new features. After discussions with teams and participants, we have decided to increase the number of sensors that can be used in the competition, right? There were concerns and complaints that 3 or 4 cameras is not enough these days for some complex situations. So we're going to raise that number. In order to allow for this, we'll have a qualification round. There will be some qualifiers, and teams that pass those qualifiers will have access to those extra sensors, to those extra scenarios to compete in the actual challenge. Another piece of feedback that we have received is the need for better demonstration tools. So it's hard to really acquire data showing how to solve some of the traffic scenarios. We have done our best effort to provide logs, human logs, on how to solve some instances of these scenarios. We're working hard in collaboration with our teams to provide like a dynamic demonstrator, like an agent that can really solve the scenarios using privileged information. And we hope to make this available once it's finished to the community. Another change, as I mentioned before, in previous years, authors could decide if submissions will be visible to the rest of the world or not. We are in situations where it feels unfair that to see that many teams are using the platform, but they are not showing the results to the world. We want to strike a compromise. We have decided that for next year, all submissions will be visible, although they will be anonymized. So whoever doesn't want to tell the world who they are, that's okay. We will have an anonymized entry showing the score that submission obtained, but the scores will be visible for each entry. We hope to basically motivate teams to keep submitting and participating in the CARLA leaderboard using this new approach. Finally, institutions are invited to run their own independent competitions based on the open source CARLA leaderboard infrastructure. So the CARLA Autonomous Driving Challenge is built upon the CARLA leaderboard, and we have made this cloud-based infrastructure open source and available to everybody. So any institution can run now variations of the CARLA challenge on their own. We actually invite institutions to do so. The first of these institutions is going to be University of Oxford. So next year, University of Oxford, in collaboration with AWS, will be running the CARLA Responsible AI Challenge. So this challenge will evaluate autonomous driving agents against new responsible AI metrics. There's going to be a call for participation that you can check on this link on the website or the QR code, and the competition will open in early 2024. This is very exciting. It's very exciting to see how new entities are organizing independent competition based on this infrastructure. We're very happy to see this. We hope that there are many more like this to come. Okay, now it's time for the fun Q&A with the teams. Let's hear about how they have solved the problems. Let's ask all those tricky questions about their approaches, and hopefully find more information about what works and what doesn't work. Okay, so we have Luis and Iago from LRM. I believe we also have Kashra in the room. Kashra, are you in the room? I heard a very faint yes. Luis, can you unmute yourself? Oh, hi.
Hi.
Yeah,
Yes, I heard him.
From the Kyber E2E team. Thank you.
Awesome. Luis, can you speak?
Yes.
Great. So let's get started. So I'm gonna start with a few questions, and then we can open to the public in the room or online to ask additional questions. So I would like to start with the LRM team, with Luis and Iago. So you guys are actually veterans of the CARLA challenge. It's not the first time you win this competition. In fact, for people who are not are new to the CARLA challenge, your team won the first edition of the CARLA challenge, track 1, 3, and 4 back in the day in 2019. Now you are debuting in the Leaderboard 2.0 as the leader of the sensor track, the most challenging competition that we have created so far. So congratulations. It's great to see you again taking one of the top positions. This year, you guys have decided to use a hybrid approach, combining end-to-end for lateral planning, along with classical modular pipeline for longitudinal planning. Why not going full-on end-to-end? Why was it important for you to leverage a modular approach for longitudinal planning? What kind of problems were you trying to address?
Yes. Hello. First of all, thank you to the CARLA team for the challenge and for the simulator. We are very happy to participate and for the results. With our experience in previous challenge, we have very robust agent using simple methods. In this case, for regression, we use simply ResNet. In the other hand, we have a very robust stack for navigate using map, and our perception is very good. But we have another agents using end-to-end driving, but this hybrid stack is performing in a superior level to the others. But in fact, the next year we can have another approach using end-to-end learning, full end-to-end learning.
Thank you. Kasra, correct me if I'm wrong, but I think this is the first time you guys compete in the challenge. Is this correct? Have you participated in previous editions?
Yes, yeah, this is our it was our first time, and I guess we were a bit late to the whole process. We maybe started 3 months ago, so we had to basically move pretty quickly to get a solution, for the submission.
Well, congratulations for claiming the top spot on the map track. I think this is a fantastic approach.
Yeah, thank you.
So your approach actually leverages language-aided perception for the detection of traffic lights and stop signs. Can you tell us a little bit more about this? It seems one of the key goals of the component was to understand the speed limits.
Yeah, I guess like as I mentioned, we didn't have the time. Our goal was to do an end-to-end approach initially, but as you pointed out, there was not enough demonstration, or it wasn't easy to actually gather expert demonstration to train an end-to-end model. So we figured we have to come up with a compromise. So basically, we tried to reuse the tools from the previous, competitions and previous entries. What was lacking, that was some of these new scenarios, there wasn't really any suitable models for that. So what we did, we relied on kind of pre-trained models from other domains. In this case, like some language models, some object detection models. We kind of put them together, set up the queries and prompts to basically fill in the gap where the models from the previous submissions were lacking, and kind of was able to provide all the information needed to at least solve most of the scenarios. Maybe not 100% of the scenarios. There are still scenarios that we couldn't really solve within the time frame. But yeah, that helped to basically fill in the gap where the previous year's submissions were not providing all the information needed.
It seems that the language-aided perception was a good idea because, in fact, your speed limit infraction counter is 0. You didn't make any speed limit infraction, so
yeah,
the technique kind of worked for that. So good. Congratulations.
Thank you. Yes.
Do you think this is overkilling, or do you think this is the right way to go? And this is a topic that has been asked already throughout the day.
Yeah, well, I guess we also think about, so there is two ways to think about this. Like if we want to do end-to-end, of course, we can't really use the models as they are. We have to retrain those. But in this specific example, especially that we didn't have too much time, we use the modular approach and a kind of a sequential process. And given that, we were able to fully utilize those models as is without really needing to change anything. It's just a matter of querying. And I have to say, our team have extensive work and basically experience on the planning side. So we leveraged our expertise from the planning side, and on the perception side, we kind of relied on the kind of what's available from the open source community and from the pre-trained models.
Awesome. Luis, back to you. Your lateral controller makes use of a bird-eye image that you synthesize from sensor data. The bird-eye view is fed into the network that serves as your planner, and that network regresses like 200 2D waypoints. Is that correct?
Yes, it is correct. It is approximately 40 40 meters ahead of the car.
I guess I have a few questions about that. Like why the bird eye view representation? Why
The
using the bird eye
virtual
view
view,
representation?
we use the virtual view representation why it is replace the map. The map, we don't have map, and I think that the virtual view is a good representation for substitution of this map. We have the surrounding information around the Eagle car, and we can rasterize the information, and it's very easy and very easy. We have images in RGB format, 3 channels, and we can use all state-of-the-art deep learning for regression. And in the end, the path is regression is regressive for the deep learning method. We can change this method and it's the same.
And correct me if I'm wrong, but those waypoints that you're generating are basically on image space, and finally you manage to lift them back to 3D. Is that correct?
Yes, it's correct.
How do you do the lift into 3D?
Yes.
But how do you convert from the bird eye view waypoints to 3D positions, to 3D waypoints?
Yes, waypoints are in world coordinate system, and we have the GPS, and using
Okay.
the pose of the Eagle car, we transform these points to the Eagle car, to the system, coordinate system of the Eagle car.
Okay, got it. Back to you, Kashra. Following up on this line of thoughts, so I believe your tracking and prediction module operates also on image space. Is this right?
So yeah, we basically detect everything in 2D. We are kind of on the top level. We don't include the height effectively. So everything is just in X and Y, 2D space. And then we track them in the 2D space and then estimate like the temporal information, like the orientation and their speed based on that.
Moving on to your planner. So you talk in your presentation about handling negotiations, and in this new version of the leaderboard, it's critical to decide when you yield to other actors. You don't want to be in the way of an emergency vehicle. You don't want to pull out of the parking lot when there is an oncoming vehicle. So could you dig a bit deeper on the use of how you thought about the design of your planner, and what's the roles, how you're leveraging inverse reinforcement learning in your planner?
Yeah, so where that works is I guess the decision part, that the part that's about yielding to other objects, that part was kind of hand designed effectively. There's a bunch of heuristics and rules based on the tracking and predictions that we had. So we track the objects, we predict their movement, and then based on that prediction, we make a decision whether we're going to be in conflict with that object or if it's not going to affect us. And sometimes we notice that we can actually, if there is enough distance or enough gap, we can actually influence the decision of other objects by basically driving in front of them. So at other times, like if it's an emergency vehicle, we should make the assumption that they're not gonna yield to us, so we should avoid them. So that's the kind of, it was more of a heuristic at that level. But after that, when we want to do actually the planning, the motion planning and finding a trajectory, at that point we did use the inverse reinforcement learning. We didn't actually, we used another source of data to train that model. It wasn't based on the CARLA data. It was based on like a data set from it's a set of open source data sets like Indy, Heidi, Roundy, like it's from I think University of Aachen. We actually train our planner based on that data set, but surprisingly, it actually transformed pretty well to the CARLA with minor tuning.
Nice. Luis, maybe let me ask you also about decision making. So your decision making model is a simple state machine with 4 states. Now, the correct behavior of that state machine depends on proper perception and proper risk assessment. So if any of those modules fail, you're gonna end up making the wrong decision. Do you have any ideas on how to make this model more flexible, more robust?
Yes, decision making depends of the perception model. Perception model needs have a good rationing, but if the perception fails, decision making fails. I think that we can use machine learning, deep learning, or end-to-end learning for substituting for replace this model. In this case, we use the detection and the perception. I think in the simulator the sensors don't fight, and in real case sensors can be filed, and I think that deep learning or another method can be backup for these models.
Okay. Now I have monopolized both of you for a long time. So do you have questions from the room or online? Otherwise, I have plenty of additional questions. So please, someone stop me.
And Hemant, we probably have time for one more question before we need to wrap up in the physical space here. If you want to go for your question you're thinking of.
So I guess my final question to both of you will be, what kind of advice would you give to new teams participating or willing to participate in the new CARLA Autonomous Challenge? So maybe Luis, you can go first, and then we hear from you, Kasra. Luis?
We need prepare a very good data set. Data set is very important for training our models and to try new models, test new methods. I think that collecting the data set is very important. And very well.
Thank you. Kasra?
Yeah, I guess I mean probably a lot of the teams that participated already know this, but this was a very challenging challenge. It wasn't really easy to solve it. You can see that the scores are not that high. So I would say don't be disappointed. Like when we started at first, like we would see our score is even below 1, and kind of we were looking at the leaderboard 1.0 and we're saying, okay, there's still a huge gap from where we are and where other teams might be. But it looks like we weren't actually that far from like uh, the best teams for this leaderboard. So I guess don't assume that others are too high. So just have trust in yourself. And I guess I add to Luis's that I think data is quite important. So trying to find good quality data, kind of diversity is at least for us proved to be quite important. Now I know it's you guys are working on it, so hopefully there's going to be more sources available. And finally, I think overall this pipeline is quite complex. So I kind of suggest others to try to build on top of the work of the past contestants. So you can basically bootstrap your work a bit rather than starting from scratch. It's going to be a bit too much work to start from scratch for this challenge.
I think those are great suggestions, great recommendation. Well, thank you to both of you. Thank you for your participation, and also to all the teams who have participated in the challenge this year. Congratulations to the winners.